In 2018, astronomers pointed their telescopes into deep space and, well, they saw an explosion that basically shouldn't exist.
Right, a blinding blue flash that completely broke all the known laws of astrophysics.
Yeah. Okay, let's unpack this because it's wild. I want you to imagine you're sitting on a blanket at a massive 4th of July fireworks show.
Sounds like a pretty standard summer night.
Right. So you look up, the shells burst, they flare up in these bright red or gold colors, and then they just sort of, slowly fade away into the dark.
Which is a standard trajectory of explosive energy, right? It's followed by a gradual dissipation. I mean, it is exactly what our physical models tell us to expect.
Exactly. But imagine that right in the middle of the show, one single firework goes off, and instead of fading, it stays blindingly bright and piercingly blue for days.
Oh, wow.
Just hanging there, searing the sky. I mean, it completely defies the physics of how a firework is supposed to burn.
Right.
And that is essentially what astrophysicists have been seeing out in the cosmos. They call them LFBOTs.
Yeah, which stands for luminous fast blue optical transients. And, in the vastness of the universe, observing something entirely new, something that actively shatters our existing models, is exceedingly rare.
So rare.
Our mission in this deep dive is to explore a newly translated scientific paper from May 2026. We're not just going to explain what these bizarre blue explosions are, but we're looking at a radical new theory involving, well, the most violent stellar collisions imaginable.
It's just crazy to think about.
It is, because understanding these anomalies, it forces us to fundamentally rethink the life cycles of the most massive stars out there.
Right, so we have this cosmic crime scene that has completely baffled people for nearly a decade now. And since that initial discovery in 2018, researchers have been hunting for more of these LFBOTs. But the numbers are, incredibly low.
Very low.
They've only definitively detected 14 of them.
Yeah, just 14 confirmed events across the entire observable sky over the span of 8 years.
I always struggle with the scale of this, honestly. Because, the universe is unimaginably huge and chaotic. Galaxies are constantly colliding. Stars are dying by the second.
It's a very busy place.
It really is.
Yeah.
So if this is a natural phenomenon, how have we only managed to spot 14? Are instruments just looking in the wrong direction? Or are the physical conditions required to create this specific blue flash just mind-bogglingly rare?
Well, what's fascinating here is it leans heavily toward the physical conditions being almost impossibly specific.
Really?
Yeah. To grasp why this event is so rare, you have to look at how it violently contrasts with a standard cosmic explosion, like a supernova, for example.
Okay, right.
When a typical massive star runs out of nuclear fuel and its core collapses, the resulting supernova takes weeks, sometimes even months, just to reach its peak brightness.
Because it's so huge.
Exactly. The energy from the collapsing core has to physically push its way out through massive, dense layers of stellar material. And then, once it finally peaks, it takes a really long time to gradually fade out.
Right, so it's a slow burn. The light curve basically looks like a gentle hill.
Precisely.
But the LFBOTs, they spike in just a few days. They go from 0 to peak brightness almost instantly. And as that firework analogy highlighted, they maintain this persistent, intense blue color.
Which is key.
Right, because in astrophysics, color acts as a direct thermometer. Like a red or orange glow means something is relatively cool, but a persistent blue.
A persistent blue signifies an environment that is unfathomably hot.
Like how hot are we talking?
We are talking about thermal radiation on a scale that completely dwarfs a standard core collapse supernova. It requires an immediate catastrophic release of energy without any massive insulating layers to absorb or cool that heat down.
Wow. Which I guess explains why the old theoretical models failed so completely.
They really did.
I remember reading that researchers initially tried to force these observations into two existing camps. Either it was some weird variant of a supernova or it was a tidal disruption event.
Right, the tidal disruption.
Which is when a black hole basically tears a wandering star apart and consumes it.
Yeah, but the math completely rejected both of those explanations.
Really? Completely?
Completely. I mean, a standard supernova simply cannot reach that extreme temperature that quickly. The energy transfer is just way too slow.
Oh, okay, that makes sense.
And a tidal disruption event couldn't explain the immediate surrounding environment we observed in those 14 cases.
It's like trying to explain a massive tsunami using the math of a dripping faucet,
That is a highly accurate way to frame it, actually.
I try.
The old models absolutely cannot account for the incredibly dense circumstellar environment.
Circumstellar, meaning around the star.
Yes. That thick fog of gas and dust immediately surrounding the explosion. When the light from these 14 LFBOTs finally reached our telescopes, the data showed that the explosion was violently plowing through a massive, thick wall of debris.
So it wasn't empty space.
No, it was tightly clustered right around the star. And normal stars simply don't have that dense of a debris field hugging them right before they die.
Right, because the space immediately around a normal dying star is relatively clear.
Exactly. So the combination of extreme temperature, the rapid speed of the flash, and this incredibly dense surrounding fog, it meant the supernova and black hole meal theories had to be thrown out entirely.
Back to the drawing board.
Pretty much.
So if standard stars and normal stellar deaths can't generate this kind of heat and leave this kind of debris, what is the absolute upper limit of stellar temperature? Like, what kind of cosmic engine runs hot enough to actually fit this chaotic profile?
Well, you'd have to look at the absolute heavyweights of the cosmos, specifically Wolf-Rayet stars.
Okay, Wolf-Rayet stars.
Yes. These are among the most massive and fundamentally the hottest stars in the universe.
How hot?
To give you a baseline for comparison, our sun has a surface temperature of about 5,500 degrees Celsius.
Right, which is plenty hot.
Sure, but a Wolf-Rayet star surface ranges from 30,000 to a staggering 200,000 degrees Celsius.
Wait, 200,000 degrees?
Yes.
That is heat on a scale that actually breaks down atomic structures. I mean, how does a star sustain that kind of temperature without simply blasting itself apart instantly?
Well, the reality is they are in the process of blasting themselves apart.
Oh.
Yeah. The defining characteristic of a Wolf-Rayet star is that it has completely lost its outer envelope of hydrogen.
Which is the standard insulation for almost every normal star, right?
Yeah.
Like a typical star has its fusion core wrapped in a massive, thick layer of hydrogen gas.
Exactly. But a Wolf-Rayet has been entirely stripped of that protective layer.
So what are we even looking at then?
What you are observing is its blazing, exposed helium core fusing heavier elements directly in the vacuum of space.
Okay, here's where it gets really interesting.
Yeah.
Wolf-Rayet star is basically like a race car moving so intensely fast and running so unimaginably hot that its exterior panels literally melt and blow off. And what's left isn't a normal car anymore. It's just the raw, blazing engine roaring down the track fully exposed.
That is a great analogy. And the physical mechanism blowing those panels off is what we call stellar winds.
Okay.
But, we aren't talking about a gentle breeze here. The radiation pressure generated by that exposed helium core is so intense that it literally pushes the star's own mass outward at millions of miles per hour.
Millions of miles per hour.
Yes. The outward force of the light itself is actually stronger than the inward pull of the star's gravity on its outer layers.
That's insane.
So the star is forcefully exhaling its own mass.
Wait. And that exhaled mass, it doesn't just disappear into the void, right? It hangs around the star.
Exactly.
So that dense circumstellar environment, that thick fog of cast-off hydrogen we saw acting like a wall in the LFBOT explosions, it was generated by the star itself.
You've got it. The star creates its own surrounding fog bank. But this violent shedding means Wolf-Rayet stars are living on borrowed time. Because they are burning through their fuel at such a catastrophic rate, their lifespan is a mere blip on the cosmic timeline.
Like, how short is a blip?
They might last only a few million years compared to, say, the 10 billion years our sun will burn.
I am guessing they don't usually live out these short, violent lives in isolation either.
No, they don't. They frequently exist in binary systems, two massive stars orbiting a shared center of mass.
Right.
And that proximity is key, because the gravitational pull of the companion star actually accelerates the stripping process.
Oh, interesting.
Yeah, the companion is literally siphoning and dragging that outer hydrogen envelope away, speeding up the transformation of the main star into that naked, blazing helium core.
But if I remember basic astronomy, a star with that much mass is destined to collapse into a black hole or neutron star anyway, right?
You're right.
Like, it runs out of fuel, the core caves in, you get a supernova. So why is this a mystery?
Well, their natural destiny is indeed core collapse. But remember, the LFBOT is not a natural supernova.
Right, because of the speed.
The light curve is too fast, the heat is too intense, the natural destiny of this Wolf-Rayet star gets violently interrupted. Hijacked, really.
Hijacked. And this is where the new paper from May 2026 steps in.
Exactly.
It takes the unexplained LFBOT explosion and this exposed superheated Wolf-Rayet engine, and it just smashes them together.
Literally. The researchers mapped out a wildly specific, almost unbelievable scenario.
Walk me through it.
Okay, start with that binary system. Star A and Star B orbiting each other.
Okay, got it.
Star A is slightly more massive, meaning it burns through its fuel faster. It reaches the end of its life, goes supernova, and collapses into a compact object, specifically a black hole.
Okay, so that leaves us with a living star orbiting a dead one. A black hole locked in a gravitational dance with a companion that is rapidly evolving into a Wolf-Rayet.
Exactly. So Star B becomes the Wolf-Rayet. It strips its hydrogen, exposes its 200,000-degree helium core, and fills the surrounding space with that thick fog of stellar material.
But the black hole isn't just a passive observer in this, right? Because it has immense gravity.
It does. And this is where the mechanics get truly fascinating. The black hole is orbiting through that incredibly dense fog of cast-off hydrogen.
Oh, man.
And as it moves through the gas, it experiences friction, drag.
Like moving through water.
Exactly. That physical resistance saps the black hole's orbital energy.
So the orbit isn't stable anymore.
No.
The drag from the gas cloud is acting like brakes on the black hole, causing its orbit to decay. It's spiraling inward.
Inward, getting tighter and faster. And hundreds of years after Star A originally died, its decayed remnant, the black hole, physically collides with its living companion.
No way.
Yes, it crashes directly into the naked helium core of the Wolf-Rayet star.
So what does this all mean? We're talking about a star that dies, turns into a black hole, and then its corpse is dragged inward by the breath of its own sibling, only to crash into it centuries later.
It is remarkably poetic in a very destructive way.
It is a macabre, multi-generational cosmic hit and run.
Yeah.
But mechanically, how does a black hole hitting a star create an LFBOT? I mean, does it just swallow the star whole?
It doesn't swallow it. The impact is a violent structural disruption.
Okay.
As the black hole plunges into the ultra-dense helium core, its immense gravity disrupts the star's internal fusion.
Right.
But more critically, the black hole begins aggressively feeding on the star's core material from the inside.
The source material actually included some visual data on this. It described an accretion disk forming.
Yes.
So you have this blindingly blue, raging star, and plunging right into it is a black hole surrounded by a whirlpool of superheated plasma that it's actively tearing away from the star's core.
If we connect this to the bigger picture, the black hole burrows in and starts consuming matter at an astronomical rate.
And what happens to all that energy?
This hyperfeeding creates relativistic jets. These are beams of pure energy and matter shooting outward from the black hole's poles at nearly the speed of light.
Whoa.
These jets literally blow the Wolf-Rayet star apart from the inside out.
A catastrophic inside-out detonation that completely explains the speed.
And exactly.
It entirely bypasses the slow, weeks-long energy curve of a normal core collapse supernova.
It is an instantaneous energy release. And because the star was already a naked helium core, the blast isn't muffled by layers of hydrogen.
The panels were already off.
The panels were off. Furthermore, that explosive shockwave immediately slams into the thick fog of cast-off materials surrounding the system.
So the blast hits that wall of gas, generating immense friction and radiation, which locks in that intense, persistent blue glow for days.
That's it. The Wolf-Rayet collision model fits the constraints perfectly.
It really does.
The collision with the exposed core provides the rapid timeline and the unimaginable heat. The pre-existing fog provides the dense environment. It mechanically accounts for all the bizarre metrics recorded in those 14 LFBOT events.
I gotta say, it is incredibly satisfying when a theory threads the needle like that. It explains the anomalies seamlessly.
It's very elegant.
But, you know, as elegant as this math is, we're still talking about a sample size of 14. I have to assume the scientific community isn't popping champagne and rewriting textbooks over just 14 data points.
No. They're cautiously optimistic, but you are correct. 14 events form a compelling pattern, but they do not establish an undeniable fact.
Right.
To verify the Wolf-Rayet collision hypothesis, we need to observe this specific hit-and-run signature repeatedly across different galaxies in varying conditions. We need a massive influx of data.
Which brings up the obvious hurdle. If these events require such a ridiculously precise sequence, a binary pair, staggered deaths, orbital decay through a gas cloud, and an inside-out black hole detonation, how do we systematically find more of them in a universe this large?
Well, the solution is heavily reliant on a massive technological leap.
Okay.
Specifically, the Vera C. Rubin Observatory in Chile and its legacy survey of space and time, known as the LSST.
I've heard of this.
It represents a fundamental paradigm shift in how we observe the sky.
Right, because from what I understand, traditional observatories are a bit like looking through a highly magnified drinking straw.
Yes.
Like you can see incredible detail millions of light years away,
Hmm.
but your field of view is minuscule. You basically have to know exactly where the explosion is going to happen before it happens.
And with unpredictable transients like LFBOTs, guessing where to look is mathematically impossible.
Right.
The Vera Rubin Observatory solves this with the largest digital camera ever constructed for astronomy. It's a 3,200 megapixel sensor.
That's enormous.
It is. Rather than focusing on single targeted points, it rapidly sweeps across the entire visible night sky.
So it's less like a sniper rifle and more like a sweeping floodlight.
Precisely. It maps the entire available sky every few nights, pulling in terabytes of data.
Every few nights.
Yes. It is purpose-built to detect things that change. Stars that flicker, asteroids that move, and massive explosions that flash and vanish.
Wow.
Because it is constantly recording such a wide field, the expectation is that automated algorithms will help us capture hundreds, if not thousands, of LFBOTs in the coming years.
Okay, so we are transitioning from finding a needle in a haystack to basically scanning the entire farm with an industrial metal detector.
Exactly. But this raises an important question. Once we build up a catalog of hundreds of these events, especially the faint ones in extremely distant galaxies, what larger cosmic trends will they reveal?
What do you mean?
Because observing deeper into space fundamentally means looking further back in time.
Oh, right, because the speed of light is finite. So if we detect light from a galaxy a billion light years away, it took a billion years to reach the telescope. We're seeing the universe exactly as it was back then.
Which turns the Rubin Observatory into a time machine.
That is so cool.
We can use these newly discovered LFBOTs to track how massive stars behaved in the early universe. Did Wolf-Rayet binaries form more frequently when the universe was denser?
Oh, I see.
Does the rate of these collisions change as galaxies age and expand? Confirming this theory isn't just about closing a cold case from 2018. It provides a brand new metric for understanding the violent dynamics of the early cosmos.
So just to recap the journey here for you all listening,
Yeah.
we started out looking at a handful of mysterious blue flashes that seemingly broke the laws of physics.
Right.
They were too fast, too hot, and too chaotic to make any sense under the old frameworks. But now, this newly translated paper gives us a mechanical blueprint.
A very violent blueprint.
Seriously. These flashes are likely the exact moment a dead star, a black hole, spirals inward on a wave of gas and burrows into the naked, boiling core of its twin, triggering an inside-out detonation hundreds of years after its own death.
It really forces a massive shift in perspective, doesn't it?
It does.
When you look up at the night sky, it is tempting to view the stars as peaceful, stationary beacons. But this research highlights that the universe is a highly dynamic, wildly violent arena.
Definitely not peaceful.
No. It is populated by interacting giants, locked in gravity, constantly evolving through destruction. The tranquility we perceive is strictly an illusion of distance.
The tranquility is just an illusion of distance. Man, I love it. Think back to that fireworks show we started with.
A single blue flare.
Yeah. If it takes this incredibly precise, multi-generational cosmic choreography like a massive binary pair, staggered life cycles, orbital drag, and an inside-out black hole detonation, just to create this one specific blue flash.
It makes you wonder.
It really does. What other bizarre, highly specific stellar collisions are happening out there right now? Hidden in the dark, just waiting for our telescopes to get fast enough to see them.